welcome back. I'm glad that you have returned, I guess. uh, yeah, I don't know, you guys. It's hard to make jokes into this thing. Okay. Um, okay, so when we last left off, we had sort of figured out how to do the determinant of triangular matrices, upper triangular ones, lower triangular ones, and the determinant of diagonal matrices. And what we found out was that, well, they're the same, and they're just the product of all of the diagonal entries, which is really nice. What we're sort of going to chase after at this point is how do you do the determinant of, like, all of the determinants? And we're going to do this sort of like using all of the properties that we had decided we would like to have in a determinant, and we're going to sort of like see how that like plays out if we're going to calculate the actual determinant. And honestly, what we need to do is we need to do some column operations, right? And we're going to do some column operations, and if we can get the column operation into a triangular form, then we can compute the determinant in a triangular form. So we can do like column operations, and here's where an idea we might have comes into play. Column operations on A, right? Because remember, column operations don't change the determinant. Well, not necessarily. I'm going to revise that statement in a second. Column operations on A, which are really row operations on A transpose, right? Because the transpose, if you remember, I can't remember the last time we talked about it, but transpose like switches rows and columns. So, well, if you switch the columns into rows and then you do row operations, that's like doing column operations on your original matrix. Now, what we might remember is that like row replacement, that's sort of like elimination method for rows, or like we'll say column replacements, right? Like of AT, or like column replacements. Ooh. The sort of like eliminate step of columns, right, on A doesn't change the determinant, which is nice. That's a really nice property. We do have like some operations that do change it, so we need to keep track of like if we do a column exchange, right? Like, because this is like, okay, this means -1, or I'm gonna say you change the sign of the determinant So when we do, if we do a column swap, we need to like keep track of that, because you know, if we do 3 column swaps, it'll go from negative to positive and then back to negative or whatever else. And then we also need to keep track of like multiplication by a scalar. Scalar multiples. Because those numbers sort of like factor out, right? And then really that's how we're going to compute the determinant, but I'm not necessarily, again, I'm not interested in like calculating the determinant of like a 9 by 9 matrix. That sounds awful, and we're going to not do it. But what we are going to do is like, okay, well, if these are the steps, what does that mean? Like, what sort of implications does that have for the determinant, and like what it can do? And here's what I'm going to say. Think about this. Okay, so if the echelon form of A transpose and remember, to get to echelon form of A transpose, we've done a bunch of row operations on A transpose, which are column operations on the original matrix A. So if echelon form of A transpose doesn't have pivots in every column, then like A is not invertible. And okay, if A is not invertible, we know that like det A equals 0. So we know this because if you don't have a pivot in every column, then you're not invertible. Okay, so, and what we said earlier was like, well, if a matrix isn't invertible, it will have a determinant that's 0. Okay, so let's think about the other way to say it. So if a matrix is invertible, well then, we could, if matrix A is invertible, then well, echelon form of A transpose has a pivot in every column, right? So we're some number of row operations on A transpose, so I would say column operations from a triangular matrix. And since it's invertible, all of the pivots in that triangular matrix are non-zero, right? And that would then imply that the determinant A is the product of det A is the product of non-zeros, diagonal entries, and also, like, it's not that simple because we did some column operations, right? So if we did some column swaps, like, and we did some column swaps, it might change sign, and if we had some scalar multiples, we might have those. So we'll say times any corrections from column operations. And the take home is that, like, well, that number then is not 0. And this is really important because this is like, I mean, from what I remember, this might be what you use determinants for in your sort of previous experience in Algebra 2 or pre-calculus, but what we know is that if a matrix is invertible, then the determinant is 0. If the matrix is not invertible, then the determinant is 0. If the matrix is invertible, then the determinant is strictly not 0. And that's big, and that's going to sort of roll us into a proposition. Number 3.3. And that proposition is just basically going to be det A, the determinant, if and only if A is not invertible. The equivalent, like you could also say if you wanted to, we'll just write that out here, equivalently, det A is not 0 if and only if A is invertible. So immediately it's kind of nice because we have this sort of like barometer to check whether a matrix is invertible or not. We can find its determinant. Now we haven't exactly sort of, we're like this far into determinants, we haven't exactly laid out sort of like formally how we defined a determinant. We've sort of identified some ideal properties and messed around with some stuff. We haven't exactly talked about how to find a determinant. We sort of went through a very vague sounding algorithm here, but we never really sort of laid it out, and we haven't sort of like mention anything about uniqueness or anything else. So right now this determinant is this vague thing, but what we do have is a really neat barometer that, like, okay, if we can compute it, if we do eventually get there, and we will, that it's a pretty neat barometer for invertibility. And actually this should not come as a surprise, because in pre-calc, you know, when we did a inverse of a 2x2, you would do like 1 over determinant times, I don't know, you would swap some entries, and if the determinant was 0, 1 over determinant is not well defined, and so we would say it's not invertible, and this sort of holds with that. Okay, so we're going to put proposition 3.3 on hold. We're going to get into, we're going to sort of make this sidebar into a couple of interesting arguments, and then kind of wrap it all up together, and hopefully have a couple of aha moments, because I understand that, like, this is kind of a mess right now. So here I'm going to talk about determinants of a transpose and of a product. So we're going to see, like, okay, well, what happens if you take the determinant of the transpose of a matrix, and what happens if you take the determinant of a product of matrices? Because these things are, like, if we can nail down these things, we can really sort of figure out how a determinant works. Okay, so, well, let's start with a theorem, and we're going to, like, work our way to proving a couple of these theorems. So here's my first real theorem about the determinants, and of course it's 3.4, and we're going to say if you have a square matrix A for a square matrix, well, it's going to be pretty short. The determinant of A is equal to the determinant of its transpose. Wow, neat. Cool. This is pretty big. Like, the transpose has the same determinant as the original matrix. If you swap all of the rows and columns, the determinant actually ends up the same. And what's really neat is, like, the row operations that we would do on A transpose end up being the same thing as column operations we did on A. So if we do row operations on A transpose, and we just sort of keep track of the scalar multiples and the swapping of rows, because again, those, like, have some effect that carries out through the determinant, we can actually get there. We're not ready to prove it yet. We can actually prove a couple of things at the same time if we get out the next theorem. And this is going to be, well, I guess the last one is 3.4, so we'll do 3.5. And this is about the determinant of a product. So for square matrices, A and B, the determinant of the product is, well, it's the product of the determinants. Which is also a really nice property to have, right? Like, you can sort of calculate each determinant individually, and that's what we're going to use it for. And if you have some matrix that's the product of a bunch of other matrices, well, you could do the determinant of all the other matrices individually, and then sort of multiply them all out. And that's the power in this. That's the real power of theorem 3.5, because we know easily, very easily, the determinants of special matrices, of our upper triangular or lower triangular matrices and diagonal matrices, right? And so if we could find a way to, like, represent some matrix in terms of, well, maybe it's a very long product of diagonal matrices, well, we can compute those determinants very simply, and then now we can compute this larger, more complicated matrix determinant pretty easily. Okay. Okay, so if we want to prove these two, we're going to need a little bit of extra help, and the sort of place we're going to start with is maybe a watered-down version of these, and we'll call it a lemma, mostly because it sounds cool, and mostly because we'll use it to prove some others. And our lemma is like, okay, so we've got another square matrix. So for a square matrix A and an elementary matrix, which we'll call E. And remember, elementary matrices are these matrices that do the row operations for me. So like swapping two rows, well, there's an elementary matrix that does that. Doing this sort of row elimination step, there's an elementary matrix for that. Multiplying a row by a scalar, there's an elementary matrix for that. So if we have a product of A, E, so if I do a row operation on some matrix, right? Well, it's the same as if I take the determinant of the original matrix and then take the determinant of the matrix that does that row operation. So in some sense, like lemma 3.6 is a watered down version of 3.5. And what we're going to do is hopefully like leverage 3.6 a couple of times, and then we'll be able to prove 3.4 and 3.5 in the next video. So we'll take a short intermission and come back together and do some neat proofs.